Okay, so let me first share my screen. So, screen. Okay, so okay, so hello and good day to all who will be watching this video. And this video presentation is my laboratory exercise number 8 in Signal Spectra and Signal Processing Laboratory. And the title of this is Filtering in AM Demodulation. So again, I am Mellard A. Lucero, 2019-333, a BSECE student of LPU Laguna. Then let us go with the guidelines in doing this laboratory exercise. So, okay. So the objective of this is to number one is amplitude modulate a periodic signal, demodulate and plot it in time domain. So we have here uh, a set of code that will be uh, that is um, that is given to us so that we can identify and see what is the demodulation of AM signal shows. Okay, so let us first analyze this code. So we have here the following exercise will introduce you to amplitude modulation and the modulation of signals using the Butterworth filter. So we have here the DSB-SC modulator. So this means that the DSB-SC means double-sided double sideband suppressed carrier transmission, and it is a transmission in which frequencies produced by amplitude modulation or AM are symmetrical spaced above and below the carrier frequency, and the carrier level is reduced to the lowest practical level, ideally being completely suppressed. So this is for the codes for that. So we have here an FC. So this is just a variable. 20 FC is equal to 20,000, which is the our carrier frequency. Then FM is equal to 1,000 for our modulating frequency. So we have here also a time domain or time variable, which is 0 is to 1 divided by 10 multiplied to FC, or the 20,000 carrier frequency, is to 1 over 1,000. So this simply shows the time interval, which will be starting in 0 and ended in 1 over 1,000 or 0.001. So the resolution here is the 1 over 10 multiplied to the FC. So this is for the time interval. Then we have here also the M, or the modulating signal. This is equal to the cosine and multiplied to the 2 times pi times 2,000 times t, or the time interval. So we have here also the AC, X, and S variables. So these are the carrier amplitude, the carrier signal, and the product modulator. So the next one here is the subplot for that. So we have here up to this point. So we have here a port 4, 2, 1. So this clearly shows that we have here 4 rows, a 2 column, and this shows the position. So for the first plot, we have here the title modulating signal. The second one is the carrier signal, and the third one will be the DSB-SC envelope. So basically, the image will be just like, so this will be the first one, this will be the second, and this will be the third. So I can figure it and show it to you later. While I after we have analyzed this set of codes. So later we will be just copying this codes to our GNU Octave so that we can see what are this codes shows. So the next one is the DSB-SC demodulator. So we have here squaring law device. So A is equal to the S squared. So this simply A is equal to the S, which we have here the product modulator squared. Then We have here also the codes for the bandpass filter. So B is equal to a set of parameters. Then also we have here the limiter. The limiting factor is equal to the 4 A and C. Then C is equal to the limiting factor multiplied to the B. So also we have here a frequency divider and D for that variable and a set of parameters for that. Then we have here also the mixer. The E is equal to the D multiplied to the S. So this is also the frequency divider multiplied to the S, or the the product modulator that we have. So also we have here the low pass filter, which is our N is equal to 5. So then we have here the PKG load signal, and this num then is equal to the butter and sets of codes or parameters for that, and DSBSCA is equal to the filter num then and E. So this butterworth code is functions to return the transfer function coefficient of an n order, which is in our code here was set to 5, and no class digital butterworth filter with normalized set of filters. So after that, we have here for the plots that we will be having. So this is just a continuation of plots that we have. So we have here a 424, 425, 46, 427, and 428. So okay. So we have here until 428. So we will be having here a 4 rows, 2 column. So this will clearly show us that we will be having an 8 plots. So which is entitled, so the first three will be having the modulating the carrier signal, the DSB-SC envelope, then followed by the demodulator, DSB, SC demodulator. So we will be having here the bandpass filter, the limiter, frequency divider, and the mixer, and lastly the low pass filter. So this clearly shows uh, the process of how can we demodulate signal. So the first part will be the DSP-SC or the modulator. So to be able to make you understand this, although I'm not expert to this, I'll show you what some terms and principles or definitions corresponds to this AM modulation and demodulation. Okay, so let's go with my presentation. So first of all, what is AM? What is AM or amplitude demodulation? So AM or amplitude demodulation is also a type of modulation. So basically we are having two types. So the other one is the frequency demodulation. Then the other one is this amplitude modulation. So but today's laboratory exercise will be more focusing on the amplitude modulation. And first of all, how can we produce or modulate amplitude? So AM generation involves mixing of a carrier and an information signal. In low-level modulation, the message signal and carrier signal are modulated at low power levels and then amplified. So the advantage of this technique is that a small audio amplifier is sufficient to amplify the message signal. So the original form of AM is sometimes called the double-sided sideband amplitude modulation, or the DSBAM, or what I have said earlier and included into the codes. So okay, so because the standard method produces sidebands on either side of the carrier frequency, single sideband modulation uses bandpass filter to eliminate end of the subbands and possibly the carrier signal, which improves the radio of message. Power to the transmission power reduces power handling requirements of line repeaters and permits better and bandwidth utilization of the transmission medium. So some popular applications of this are broadcast transmission and airband radio. So AM is still widely used for broadcasting. So we all knew of that. So we have here AM, EM, AM radios. So we have here also the airband ranges. So VHF transmission for many airborne applications still used and in AM. So this basically, how can we the signal amplitude modulation. So the next one, or the next part of these of this module or presentation is we will be filtering in AM demodulation. So by the way, I'm just explaining this because this is also a part of our laboratory exercise. So I forgot to state earlier that we have here the reflection on the activity. So instead of doing this in written, we will be just explaining this through this medium or presentation. So what we have here is what can you observe on the given signals, then how AM modulation is being conducted. So this is the first part that I am saying to you. So this is for the amplitude modulation. Then the other one is the filtering in AM demodulation. So this is also the how AM demodulation is being conducted. And then lastly, what are your general observations? So these codes that we have here is really essential in doing this, understanding this AM modulation and demodulation. So I'm sorry, the details and explanation is just so moves back and forth because uh, ideas are said to be just like that. So, but the main point here is through this AM modulation, we will be having this process. So first, we will be having an input signals. Then this signals is processed, then or basically demodulate to produce to you the original, or the said to be the original signals that the the input or the source trying to convey into the output or the receiver of that signal. Okay, so anyways, I'm just explaining what is the filtering in AM demodulation is. So we have here the demodulation. So demodulation is a process achieved by sampling the AM signal at carrier frequency. So amplitude modulation, AM, is defined as modifying the amplitude of the carrier wave according to the message or information signal. So basically, we have here three methods used to demodulate AM signals. So the first one is the envelope detector. So I will be not in detail explain it to you, but I'll just tell the initial or the basics explanation for that. So the envelope detector is a very simple method of demodulation that does not require a coherent demodulator. So the other one method, and the second method is the product detector. So this multiplies the incoming signal by the signal of a local oscillator with the same frequency and phase as the carrier of the incoming signal. Then lastly, the synchronous detection, and this uses many more components than a simple diode detector, but in view of the uptake of integrated circuit technology, it is very essential to incorporate this form of demodulator into many radio receivers for almost zero and incremental cost. So, to be able to explain more, let us show what is this set of codes or the process of modulating and demodulating signals using the Butterworth filter. So let us copy this whole codes and paste it on our GNU Octave. Okay, copy. Then open our GNU Octave. So basically, I'm sorry, we will be doing it in editor, then paste our codes. Okay, then try to run it, and this is our OE8. So I will be just saving this as code directory. Then let us wait for it. Sometimes my PC is slow. Yon. Okay. So so let us explain this sets of plots that we have. So just like what I'm saying earlier, so we have here 4 2 figure. So we have here eight plots. So these are modulating signal, carrying signal, DSB, SE envelope, bandpass filter, limiter, frequency divider, mixer, and low pass filter. So we can see here that these are all sine waves because ended in zero, and so just like what we have in the parameters of our time domain time interval. So we have here to start at zero and ended in 0.001. So we have here a point zero. So the resolution is also typed earlier. So causing it to shows or indicates plots that's just like this. So what we I am trying to tell. So we have here first the modulating signal. So the process is our input signal is carried out to our carrier signal here. Then later, then when these are combined, this DSB-SE envelope is produced. So in able to so that is the time we are modulate our signal. So after doing this, we are producing this DSB BAM, or the double-sided sideband amplitude modulation, or DSBAM signal. We will be demodulating it by this set of signals. So first is the bandpass filter. So this is what it looks like. So this process has to screen out frequencies that was too low or too high. Then after that, we will be having the limiter. So this limits the signal within allowable thresholds value. So this is the purpose of the limiter. Then another one on the steps of the modulation is the frequency divider. So these functions to divide the frequency, divide the frequencies. Then later, resulting signal will be combined by the mixers to the modulated signals. Then lastly, low pass filter removes the carrier signals to recover the original signals, or the original audio signals that we are trying to convey on the first place. So okay, so this basically this plots only shows the how can we or the process in modulating and demodulating AM or amplitude modulation signals. So hopefully you have learned something from this video, and thank you very much for watching. Ingat po kayo lagi, and maraming salamat po.